like to welcome everyone here today. This is, I think, an exciting time for us because this kicks off this new Distinguished Speaker Seminar Series. And I would like to thank a couple of people. First, I'll say a couple of thanks. First is to Floor for providing the support for the seminar series. And the second is Mihai Sikatu and Alex Dean, who have been the people pulling this series together. And you'll hear from him in a moment as he introduces the speaker. What I'd like to do first is just to recognize Alicia Taylor, who is a structural engineer from Fluor and also a NC State graduate, to just say a few words in your support. Alicia, please.
Thank you so much for having us here today. Like I said, I am an alumni from NC State, and I currently go to the distance grad school here now. And I'm a staff engineer with Fluor Power for the past 3 years out of the Charlotte, North Carolina Power Group office. Just a little bit about Fluor. We are a Fortune 150 company. We're responsible for engineering, procurement, construction, and maintenance of industrial facilities around the world. We work out of 5 continents in 16 countries, and I believe about 30 offices there. So there are a lot of opportunities. We have a lot of room to grow. There's a lot of places to go there, and it's a great company. I will be here for a few minutes afterwards, or for a while, as long as you want me to be here, to talk to you about Fluor and all of the opportunities there. Once again, we really appreciate doing this. We are committed to a long-term developing this with the engineering companies and here at the College of Engineering in NC State. So thank you once again for allowing us to do this.
And now it's my pleasure to introduce Dr. Kok-Meng Lee, who received his MS and PhD degree in mechanical engineering from MIT in 1982 and 85 respectively. And he has been with Georgia Tech since 1985 and a professor of mechanical engineering. His research interests into system dynamics and control, robotics, automation, and also mechatronics. And he holds 8 US patents. Dr. Lee is a fellow of ASME and IEEE. He's currently the editor-in-chief of IEEE ASME Direction on Mechatronics. And he has held representative positions with IEEE Robotics and Automation Society. He founded and chaired technical committees and numerous international conferences, and on the AEM Conference Advisory Committee. And his awards include the Presidential Young Investigator Award, Sigma Xi, the Junior Faculty Award, International Hall of Fame New Technology Award, Woodruff Fellow, Faculty Fellow. He was also recognized as an advisor for 7 Best Student Awards and the Best Series Award. So now, without further ado, I'll give the award to Dr. Lee.
Thank you very much for inviting me to give me an opportunity to share some of my research with you. I have been here about 4 years ago, give another talk. So today I choose a topic that try to completely different from what I have said before. So now the outline is relatively simple. My talk, I'm going to give you some background and trend, and basically said what why working in this area. Because I'm from mechanical engineering, and if I try to present all the mechanical engineering equation, I think most of you are going to fall asleep. So, I choose 3 practical applications which I think will be able to encourage a good potential future collaboration between ME and WE on national project and international project as well. So the 3 topics that I also chosen in such a way that they present different kind of computational using different kind of computation methods, and also cover different kind of perspective. Now I show the timeline from 1980 to 2010. The reason because I actually joined MIT as a graduate student in 1980, okay, and became a faculty in 85, and working on that area since then. Okay. Now, this timeline will give you a pretty good idea why I was working in this, choosing this as a topic. Okay. Now, as I mentioned, I became a graduate student in 1980, and I actually built my first computer in 1982. And you can see at that time it's Z80, okay, and 8K memory. I was very proud of that. But of course, nowhere compete with current technology. Now, the other three pictures you can see is that I spent a lot of time since then. One of the things that one of the pictures you see is I give a talk. I give a talk on this topic, the topics on vision system and also on actuators 4 years ago. And at that talk, I spent most of the time on the hardware. Okay. Now, as you can see, in between 80 and 90, we are actually struggling a lot with computer memory and time. And a lot of you can feel feel the impact of hard disk development. Every day, I'm sure that at least myself, okay, every weekend I look at Fry or Best Buy on the price of hard disk. I can easily see the price coming down drastically, and then the memory storage increases. But what you don't see, a lot of you don't see, is what happened behind the 1990 to 2000. Okay, we see a lot of information highway because of internet and web, but the technology behind it is a lot of people is not aware of. Okay, so that's also the year that I spent a lot of time in one of these projects working with Lucent, producing fiber that enable the information highway. Now the other, these are more recent work that I have been working on. Most of these problem is actually human-centered, okay, and also because of bio-inspired. Okay, so I choose three different kind of these three different topics to talk about. Sorry, I think there are some problems. Now, one of the problems that okay, I was looking at is in this area is that in the early 80s, I find that a lot of new products that require interdisciplinary, okay, and also a lot of creative product. And more important that, as you can see in my subsequent presentation, there are a lot of these new areas require different kind of resources, typically that individual department cannot afford to. Okay. Now, more recently, you can see that NSF, a so-called blue ribbon panel, trying to emphasize on simulation-based engineering science. And this is a very, very important area, in my opinion, that because it provide important means to understand control system, and very complex system. And you can see a lot of this new technology cannot do without very good simulation-based engineering, and you'll see in some of my examples. Right. Now, so a lot of people thinking of simulation, and the way that I see simulation consists of actually 5 parts. Okay. One is that, of course, we come up with concept, right? And then we try to understand the physical phenomenon. And a lot of time that is cannot easily see from experimentally, and we need to use some theory to help understand. Second, of course, we build mathematical model represent abstraction. And third, we come out with computational model. Now, in the earlier day, you can see that because we are struggling with computer time, so a lot of our models are relatively simple. Okay, we use lump parameter, but it had been at least 30 years ago when I was doing a lot of work that relies completely on lamp parameter. So I think because of the computer technology advances so fast that we can do a lot more than just simply a lamp parameter. Okay. So for that reason, this talk focus on mostly computational model. And then, of course, garbage in, garbage out in the computer program. So it's very important that we're able to validate and also to verify. Now, I particularly make it clear that this validation and verification are two different things. Okay, at least in the course of doing research, I want my students to clearly do both when they're dealing with a computational model. The first validation is that we're trying to make sure that the mathematical model actually representing the physical system. And then the second part is once you have that, okay, then you want to make sure that the model is accurately computed. Okay, so these are the two parts. Right? Now, as I mentioned, I'm going to talk about these three examples. Okay, the first is fiber optic manufacturing, and the second is related to magnetic field. Okay, and then the third is more the human center. Now, I will start out with these three areas using three different methods. Okay, now the first one is using finite difference. This is one of the very simple fundamental computation. And the second is we all know is finite element. And the third is more recently is so-called meshless. It's almost identical to finite element except that there's no mesh, okay, meshes. So you will see in each part, okay, I was using some of these because I'm talking to electrical engineering students, so I try to focus on application aspect of it, and most of these you can find in my paper. Of course, you will see that a lot of these computation except the commercial finite element, we develop our own code. Okay, right? Now, the first one I'm going to focus on use of finite elements. Okay, this is one of the most commonly used in the early days for thermal fluid. Okay, now as I mentioned earlier, okay, in the early 90s to 2000, and fiber optics actually is one of the very important area. And in the earlier days, okay, most of the fiber they are drawn from 1 centimeter, okay, 1 meter long glass rod, okay, and then draw into 125 micron. This really a very complicated problem, involve mechanical, electrical, and chemical engineer to working on this project. Now, during the earlier 90s, you can see that the demand for fiber, okay, long fiber, is tremendous. So in order to draw large fiber at a low cost, there are a lot of proposals. Yes, one of them, of course, is the most important one, is that instead of trying to draw from 1 centimeter glass rod, why not drawing from a large diameter glass rod? That means that if you increase 10 times, you can see that you have 100 times increase in length. Similarly, that we want to draw it very fast. These sounds are very simple, okay, but it means that the science, okay, and the science and technology is completely different, because originally we are looking at 1 dimension, now we're looking at 2 dimension. And more important is that we don't even know, okay, in the past when you're drawing small diameter fiber, you know for sure the diameter become 124 micron once you leave the furnace. But once you increase 10 times and drawing at high speed, you have no idea where the fiber consolidate into 120. Okay, and now this has been a lot of very interesting joke in the industry, and it's a real joke in the sense that now I see the fiber, okay, typical process, putting glass rod and then draw into 125 micron and then put in coating and then a lot of control going on after that. Okay. Now, the way to draw the fiber is that you pull the fiber. Okay. The faster you pull, the thinner the fiber. It's just as simple, and it's a very stable process. What happened is that in the early 90s, a lot of people tend to using lump parameter without realizing that it's just 2 dimension. So you see that it's using a lump parameter, assuming very simple isothermal process, very simple temperature nodes. Okay, you can see that.